and he's going to talk about small denominators and hard implicit function theorems. So go ahead.
Okay, so thank you very much, and sorry because of the delays, etc. And let's see if I can pass the page. No, I cannot pass the page. All right. So what is going on here? Jeez. So this is one of the things that happens when you change things. So let me just try to say a slideshow. And for some reasons, this is, okay, now it's starting to collaborate. Okay, very good. So let me try to sort of give the usual disclaimer, right? That I have been trying to give a pedagogical thing. So, you know, sometimes the things are not as sharp as they could be. And then, of course, I will be omitting quite a number of important facts, right? And anyhow, so today what I will try to do is maps of the circles, and I will be following very closely Jürgen Moser's lectures in '66. And then, this will be followed up by some other applications to KAM next week by Alex Saro, not next week, in 2 weeks. And then basically the complement of what I will be talking about today will be described by Marian Gidea. So he will, I mean, it's not the complete complement, but he will be living in the complement, etc. And then Yachi Yang will be explaining significant extensions of these ideas to infinite dimensional systems and even things that don't have any good dynamics. Okay, so in the previous lectures, we discussed how to find, I mean, the philosophy is kind of the same in the sense that we are going to be trying to find landmarks that organize the long-term behavior. But we have discussed periodic orbits and their stable and unstable manifolds and then homoclinic phenomena. But now I want to describe several new phenomena, which is the quasi-periodic invariant solutions or invariance tori. And then this is sort of increasing normally the game because we need to get some analytic tools, and surprisingly, things like number theory play a role. Okay, and there are quite a number of other things like stable. I mean, and you can ask immediately what are the stable and unstable manifolds and their homogenic phenomena. And this is an order of magnitude more complicated and much more interesting, but I will not be able to cover it. So this is one of the things I have to tell you, okay? So now, some propaganda, I mean, if you want to look, there are other sources. So in particular, I gave a proof of the KAM theorem, which is suitable for undergraduates. And actually, I have tried it with undergraduates. And in about 3 hours, if you have taken undergraduate real analysis and complex analysis, then the first part is a reminder, and then the second part is another reminder. And of course, I also prepare a tutorial on the KAM theory, etc. So, I mean, the usefulness of this paper is that it doesn't present a proof, it presents several proofs and compares them. And then, of course, the main reference for today is this wonderful set of lectures by Jürgen Moser, in which he does not only the beginning of KAM, but he also does PDEs. And I actually use this couple of lectures when I am training students on how to write good papers and how to do good writing, and then of course I remind myself to try to accomplish something like that. Okay, so let me try to describe the situation of what is a quasi-periodic orbit. So when you have a sequence, then you say that a sequence is quasi, I mean, and again, the philosophy is going to be a little bit different from before for many of the things that people do in dynamics. In dynamics, people try to construct all the solutions, and then they try to sort of find the solutions that are quasi-periodic. In this, what I want to do is the opposite, is to start thinking about the set of all quasi-periodic functions and then finding the ones that are solutions. And this is advantageous in the sense that it doesn't require to study the dynamics, and it's advantageous in the situations where the dynamics is not well understood or people don't know how to construct dynamics, like for example in ill-posed equations or in equations delay equations where the constructing the dynamics is really complicated. So quasi-periodic functions are the functions that can be expressed and I find the first type of the day, which is this would be a k rather than an n, right? So I am summing in k, and then there is a k missing here, okay? If people can see the things. And of course, you can write a quasi-periodic function as people call this capital K the whole function, H-U-L-L, and then basically you are sampling the whole function at regular intervals advancing with a frequency omega. So there is an internal phase, and the internal phase keeps on finding, etc. And then you get these things over here. And then it's very easy to remark that a function, a quasi-periodic function, is an orbit of a map, if and only of a map F, if and only if it satisfies this functional equation, which people in ergodic theory call it the subfactors, or whatever you want to call it, or semi-conjugacy. I mean, I like better factors than semi-conjugacy, because semi-conjugacy, then you have to say from K to A, it's not a symmetric thing, okay? And this is the equation that I will be talking about all the time. Okay, so the way to imagine this is that you have like the perfect copy of the torus, and then you have the real torus in real space, and then you have to sort of find the dynamics. This should be lowercase f. But basically, the dynamics, if you have a point in the range of k, then you hit it with f, and then you get another point in the range of f in such a way that and then the image is more and then it's a point in the range of f, and the origin is basically displaced by omega. And you can see that, I mean, under mild conditions, like the omega is irrationally related, which you can have without any loss of generality, then these equations happen if and only if. Let me just try to say these things over here, right? Okay, and that's exactly what I want to try to say over here. And again, this is a little bit different than what the typical dynamics people do, which is to construct all the solutions and then find the periodic. I start from the quasi-periodic and then try to find the ones that are solutions. And this makes sense even if you don't have any idea of what the dynamics is. Like if you're talking about quasi-periodic, if you're talking about ill-posed equations, people have been finding special solutions in ill-posed equations for a long time, like traveling waves, etc. And depending on how the ill-posed equations are derived, then this may even make physical sense. All right, so before I start doing things, I am just going to start, this is not going to be in the subject, etc., but I am going to be going over background. So this is the dynamical interlude, etc., which is some things that are well known to people, maybe, or maybe not. So I will be talking about Diophantine numbers and Banach spaces of analytic functions and cohomology equations. So these are things that are a little bit well known, etc. So let me tell you what I mean by a number in RD when to be Diophantine. So a number frequency is Diophantine when basically what it means, of course, if you have any rational numbers, then you can get approximate resonances, because every number can be approximated by rationals. But the thing that you want to understand is that if you want to find an approximate rational, then you have to have crazy numbers, right? I mean, this is the game that people always try to do. If you look into these papers, then they say, well, you know, if you take the birthday of the president and the birthday of the day, and then you put the verse something or another in the Bible, and then you combine them, then you get 0. And then people say, oh, this means that this is a prophecy or something. Well, maybe not if you have to use these weird numbers to combine them with another. So everything can be getting crazy combinations, but the Diophantine numbers, the Diophantine frequencies are those that you can get all these crazy combinations, but then you have to use really high numbers, right? Okay, so you have to make it very quantitative. So the fact that you can get all these combinations, okay, and of course I notice another typo. So these Diophantine numbers are very abundant in the sense that you need to satisfy different conditions, and of course over here this should be a minus, right? And so you have all these conditions, etc., right? These things have to be smaller. So when these inequalities fail, when the inequalities fail, they fail, and this should be a strict inequality. I apologize. But geometrically, you realize that this set over here is a slab, and this slab has a width which is going to 0. And if the width of the slabs goes to 0, when you look at them in a ball, then they have very small measure. And therefore, you find that these Diophantine numbers are almost everywhere. That's the argument, etc. And when d is equal to 1, this is a very interesting theorem that I wanted to mention. And I also found another mistake over here. So when d is equal to 1, there is a very famous theorem by Liouville, and then it was dramatically improved by Roth, which tells you that if you have something that satisfies a polynomial equations with integer coefficients, then it is not 0. And of course, I mean, the thing that I wanted to say is that then omega is Diophantine, right? And omega is Diophantine of, this is the improvement. So Liouville proved that it's Diophantine, and the Diophantine exponent depends on the degree of the polynomial. And then the vast improvement by Roth, Klaus Roth, was that he could prove that the Diophantine exponent is independent of the degree. And it's the number Euler, the E 2.71 was proved by Euler to be Diophantine because he proved he found a very dramatic continued fraction expansion. If you have seen it, is 1, 1, 2, 1, 1, 4, 1, 1, 6, etc. Right? So it's a continued fraction expansion, and the denominators don't grow, and the terms in the continued fraction expansion grow very slowly. So Euler found this continued fraction expansion, and then it proves the things. It's an exponent. Euler E is a Diophantine number with a very good Diophantine condition, and then pi is also a Diophantine number. And the exponent that was proved it was proved in the 40s and by Mahler, and then the optimal exponent doesn't seem to be known. I mean, people keep on, I think that the record now is around 7 or so. This tau is more or less the things over here. And the geometry of the, so this is something which I want to also mention, is that when you have approximate reference resonances, they repel each other, and that these bounds, this is something which is interesting to remark, is that these bounds cannot be saturated for all Ks. It's very rare that get saturated. And the reason is that if K gets saturated for some K, then when you take a neighboring Ks, then the neighboring Ks, they satisfy this identity, etc. So when you are in neighboring Ks, then you can cast off the K, and then things start to be like if they were small numbers, right? And the small numbers, they cannot be very well approximated. And this is a very easy numerical plot of the things that you get for the golden mean. I should have put that this is the golden mean. So, you know, you put the golden mean, and then you put the omega k minus n, right? All of it to the power -1, and then you get this beautiful picture. And if you look at this beautiful picture, then you see that things are growing kind of linearly, right? That's the thing. But then these numbers have a very big, have a very large structure. So to speak, if you squint your eyes, then this part is more or less the same as this other part scale, and all this can be made precise. And there are quite a lot of beautiful things. But the thing that I want to mention is that these things, so now that you get a very small divisor, then the neighboring ones are very small, right? So that seems to be, that's a very important feature. And then in a space of analytic functions, so let me try to describe, actually I think I have even put a proof of this, let me see. All right, so this is the Liouville. I mean, I even have put a proof of, I seem to remember to have written a proof of this, but I don't see, maybe I have the, let me stop the thing for a second and then I see if I am doing the right thing. Okay, sorry about this, yes, so I think it's okay. Well, I had the proof of this Liouville theorem is not very hard, so well, anyhow, let me just try to sort of skip it. So this is one of the ingredients, and the other ingredient is that you talk about analytic functions, and then the way that I will be talking about them is I will just take the supremum, and then you consider analytic functions in a domain that extends to a domain rho, and they're analytic and they extend, and then I take the supremum. And if you take the supremum norm for functions that are continuous on the boundary and analytic in the interior, then
Rafa, we don't see the slides. We don't see the screen.
Huh?
We don't see, you're not sharing the screen.
Oh, I'm not sharing the screen. Okay, sorry about all this. Blah, blah, blah. So let's see if I remember. No, okay. All right, so I'm sharing the things now. All right, so this is the, now is it okay?
Yes.
All right, very good. So this is one of the things that I want to discuss. So this is the spaces of analytic functions. So it's analytic functions in a domain that, so they are functions that they have some periodic things, but then they extend in the complex a little bit. And the intuition is that the larger the rho is, the more that they extend in the complex, the more regular that they are, right? I mean, and this is related to Fourier series and so on, the more regular that they are. And if you have a function, you can write it in Fourier series and you can recover the Fourier series using the Fourier formula. And then this is something that I will use quite a lot, which is the Cauchy bounds, which is that you can estimate the size of a function in a slightly smaller domain. I mean, remember that this index tells you how, this is an index that tells you more or less the size of the domain. And that if you lose a little bit of domain, if you make the domain slightly smaller, then you can estimate the bounds by the derivatives, etc. So this is something which is the mysteries of complex analysis. I mean, in real analysis, we spend all the time telling the students that the size of a function doesn't tell you anything about the derivatives, but in complex analysis, then it does, but in a slightly smaller domain. Okay. And then the Fourier coefficients are very closely related to the analytic functions. If you have analytic functions that extend to a domain K, and I should have put over here UK, there is a constant here, which for some reasons I forgot. This U rho K should be also there, so sorry about all this. Okay, so they should be bounded. So they are controlled with this exponential factor, and they are controlled in exactly the same way as the derivatives. And then the cohomology equations, this is basically our workhorse, which is that I give you a function which is analytic, I give you a Diophantine number, and then I try to find another function that satisfies these things, which is a local equation. So this is a non-local equation because it involves differences, right? And then I want to show under which conditions there is a there is a function here, there is a solution that satisfies that. And you realize very quickly that if you have a solution of this equation and u is going to be even halfway reasonable, when you integrate over theta, these two things disappear, right? So there is a constraint, which is that the integral of eta has to be 0. Otherwise, there is no way that you can get anything even halfway reasonable, right? And that's what I want to say. So that this condition, this equation 2, is equivalent if you take Fourier transforms. The Fourier transforms behave very nicely under displacements, and this is the thing that happens with the Fourier transforms after you displace, and this is the function itself, right? So this is the things that happen. And so this equation is equivalent to this set of equations, and then you realize that for k equal to 0, then you get uk minus uk, which is equal to u0 minus u0, and then this is u0, so this is a constraint. So the solvability of these equations has a constraint, and at the formal level, then you have you can solve this for uk equal to 0, and then the u0 is free. Okay, so at the formal level, then you realize that you have one constraint, but then you have freedom of solutions. This is exactly like what happens when you are doing finite dimensional linear algebra. If your equation has a constraint, then you have more solutions than you wanted, right? I mean, so you have more solutions, and exactly the dimension of the dimension of the kernel is the same as the dimension of the constraints. I mean, this is what happens when you're doing n by n matrices, right? Okay, so this is nice, and of course this formal solution. So this solution is purely formal, but then these are the estimates that you get. So it turns out that you get an estimate that you can estimate u in terms of estimates in eta, but you can estimate it in a slightly smaller domain. The thing which is so this is done so this was done in 76 in Rusman, and so this was done by 76 in Rusman. So I am going to give a very simple proof of a slightly worse result, right? And so that you can start seeing how it works. So when you have u, then you realize that, I mean, if it has a Fourier series, then you can write all this as uk and the norm of this function. So this is a using triangle inequality, right? Okay. And then uk is related to eta because of all these things with small divisors. And I noticed that there is a 2 pi I missing. Sorry about all this. Okay, and then this is the uk, and these things over here is the norm of this object there, right? So this is the norm of this function here, and then eta k, and now I use Cauchy bounds, right? And this term over here cancels the k row, right? And this is the only things that you are left. Yes. So very elementary and so on, and then the only thing that you are left is you have to sum, you have to estimate a power. You have to estimate a power dump with an exponential, and the exponential is delta, right? And then the dimension center, if you do the straightforward estimates and you use if you use straightforward estimates, right, then you do the estimates in power, in, so to speak, in polar coordinates, right? And then you sum along the radius, right? And this is what you get, and then the dimension b. I put so this is what this very simple-minded argument gives you. If you do the arguments in a correct way, like Rusman did, if you do the arguments in a correct way, like Rusman did, then you get rid of this extra factor, of this extra exponent d. Okay, but this is very subtle, so you have to use the fact that. So I can tell you, since I have a very sophisticated analysts in the audience, I can tell you that the argument is this argument that the resonances repel each other, and then you have to use a Littlewood-Paley decomposition. So since Littlewood played a role in the last lecture, so Littlewood-Paley dividing the Fourier analysis in scales of 2 to the n, then you can see that in scales of Littlewood-Paley, in exponentially growing scales, you can only have one big denominator, and the others have to be kind of okay. So that's more or less the idea of Rusman. Okay, and so let me try to go back to the equation that I had before. So remember that, so now let me go back to the things over here. Now that I have comparative equations, I can tell you what the physicists always try to do and what was historically tried to do always, which is to try to do perturbative solutions. And when you try to do perturbative solutions, this is what you get. You get these solutions, and then you get f as power series in epsilon. And then once you get f as power series in epsilon, then you get the solutions. Then you try to get h as power series in epsilon. Okay, so the traditional perturbation method would be to change the frequency, right? So this is what was done originally, and this is when you talk to a physicist or to an engineer, this is what always they try to do first, okay, which is to try to get power series of h and power series in the frequency. When you change the system, then the frequency should be changing, right? And then you get all these things. And then there is the counter term method or listed method, which is that you try to find, you try to modify the equation in such a way that the frequency remains fixed, okay? So this is a little bit more sophisticated and a little bit more artificial, but it's actually quite a good thing that also happens in lots of applications, because in lots of applications, people try to sort of, I mean, if you're, for example, organizing a radio or organizing an antenna, then you want to keep the frequency fixed, even if the nonlinearity comes, and then you need to modify the design a little bit. Okay, so there is a small proposition that in both cases, then you can get the perturbative expansions defined to all terms, to all orders. And the reason is because if you equate like terms on this equation, right, this is the equation. If you look at the terms of order n, then you get a term that comes from order n over here, and a term that comes from order n here, and another term that comes from order n here, and another term that comes from order n there, right? So that's basically the things. And this is an equation that you get. You get Fn at Hn composed with T of omega 0 is equal to omega n plus Sn, right? And these are things that have been computed previously, and these are all the things that are computed previously. So that's the equations that you get. And for the counter term method, this is what you get once you start doing the things, and then you get all these things. And and there is no omega n here, sorry, that's another typo. In the counter term, then you get all these, sorry, there is no counter term there. Okay, now the interesting thing is that if you are proceeding in order, these things are known, and then you get the omega n, so that the average of this is equal to 0, and then you can solve you can solve for the h. And over here, this term, and I apologize again, this term should not be there. Then you can choose the lambdas in such a way that the average vanishes, and then you solve the cohomology equation. Okay, so this is more or less what people have been doing, etc. There is one small theorem that I want to prove, which, I mean, I am maybe not going to prove it, but the traditional series diverges. I mean, typically, if you get a family, which is, I mean, unless you choose the family, and I can explain later on, we will see why this is the case. But this traditional series diverges, except if you pick families in an infinite dimensional set. So unless you put infinitely many constraints in your family, then the traditional perturbation series is going to diverge. And then otherwise, the Lindstedt series always converges. If you have, I mean, again, I am putting the hypothesis that omega 0 is Diophantine so that I can solve the cohomology equations, right? Yeah. And actually, we will prove the second theorem, and the first theorem I will give some hints, etc. I mean, I'm putting it because, I mean, you know, if you talk with engineers, then they always, I mean, I had these seminars in the school, etc., where people were claiming that they converge and they don't, but it's not too bad. I mean, they diverge, but they diverge very slowly. I mean, these people are not complete idiots, even if you use this, but they know what they're doing. And I mean, divergent series are perfectly reasonable in many cases if they diverge slowly, etc. So if you're trying to do antennas or something like that, then it is whatever. And the divergence of this series actually was studied by Adrian Bustamante, so he can tell you a lot of that they diverge, but not very badly. Okay, so let me try to describe the counterterm method, and I am going to treat it in a non-perturbative way. So what I am going to do is to study these equations, and I put in blue the terms that appear that are the unknowns, and then you try to get an approximate, so you have an approximate solution, and then you want to try to get a true solution close by. All right, so the thing that I want to describe all this business, that there is a solution, then the first thing that you do is that you do an approximate solution. And I am introducing kind of here the functional analysis point of view. I think that this is a functional that depends on an unknown h, and that depends on an unknown lambda. And h is much more complicated in the sense that h is a function and lambda is just a number, right? Or a vector, yes? Okay, but there are two unknowns that I have to determine, and then I have an approximate solution, which is E. So then you try to get corrections, and then you want to get something that kills them a little bit better, and this is what you do in the Newton equation, right? And before I start, and let me tell you that if you give me this, right, if you give me that f plus lambda is small, then you also have to give me this other thing here, right? Which is what I obtained by taking 3 and taking derivatives of 3, right? Okay. So if you give me 3, then you give me the, and of course, if you are a real analyst, then you say, well, this doesn't give you anything, right? Because then this is dE, and dE doesn't need to be small if E is small. But I am a complex analyst now, and then if I am a complex analyst, the fact that E is small tells me that D is small, right? So there is a different point of view, etc. So that's the story, right? So this equation over here is very interesting. Huh? Yeah. All right. So this is the thing over here. So let me try to see if I can get. And the Newton method gives you this. So when you change, this is the equation, right? And if you change lambda a little bit, this is what you get. Right? You change lambda, it's a constant, so lambda composed with h. Then you change f a little, then you change delta, right? And delta, this is the first order effect of what you get when you change delta, and this is the first order effect that you get, right? Okay, so that's what the Newton method, and then you say, ah, but you're cheating me. This is not the cohomology equations that you were telling me, because this depends on the places that you were doing. But on the other hand, I can use this equation that I have been taken away, but taking derivatives, right? And then you write delta is equal to dHW. So this is my new equation, right? So I am seeking delta, but now I am seeking W, which is related with this. But then the interesting thing is that once you start putting this, then this equation that I had over there, df dHW, using the things I can write it as dH plus dE, right? Okay, so this is because of the equation 4. And now the thing that I am going to do is I am going to ignore the dEW, because I am going to wave my hands very vigorously, and I am going to say that this is second order, right? Because W is a small correction and D is a small correction. Again, I am using my complex analyst point of view, right? So D is small, right? And W is small, so I am ignoring that, and this is what I am doing, right? And so this is my equation, and this equation that I have over here after you move things around, and I should not have this parenthesis there, it becomes just a cohomology equation. So, and remember that the things that I have to choose sigma and I have to choose W. Okay, so I have to choose sigma and I have to choose W. So the way that I choose sigma is I choose sigma so that the average of this is equal to 0, right? And then I choose W solving the cohomology equation, okay? So this is the algorithm. I kind of derive the algorithm by waving my hands, etc. But then after a while, I will show you that this algorithm actually works and it actually goes well, right? So this is the algorithm. And I put the algorithm over, all right, so there is another mistake. Oh boy. All right, so the algorithm is basically you compute f composed with h, then you compute this, etc., then you compute this other, then you compute b, and then I put over here sigma, which is be, I mean, this should be divided by b star, b divided by b star, and then you solve the cohomology equation, and then you put delta, and then you have sigma. Now, what are the interesting, so this is a very interesting algorithm, and basically is what I described in words. But I am being very explicit now, and I just point out that this has 9 steps, okay? And for the people, there are some steps, for the people that are not color, I apologize to the colorblind people, but some steps are color-coded in red and some steps are color-coded in blue. And the reason is that the steps that are color-coded in red are very fast if you have H discretized in a grid, and the things that are color-coded in blue are fast if you have things discretized in Fourier series, right? So all the steps and the ones that are in black are fast any way that you like to do them, right? So the interesting thing is that if you discretize H in Fourier modes, then, well, order n storage is required, and then all the steps in blue are order n operations in Fourier, and then the steps in red are order n operations in grid, right? And then you can do all these things extremely fast in either way. I mean, of course, when you switch from Fourier to the grid, then you have to pay a price, but the price is fast Fourier transform, which is order n log n operations. And this is order n log n, but it's not a theoretical order n log n. I mean, it has a very good constants actually, you know, and people have been designing. I mean, if there is an algorithm that it's well optimized nowadays, and it's even optimized in hardware, is the fast Fourier transform. And then there are all sorts of chips that do it, etc. So that in reality, it's n log n is an understatement. So anyhow. And if you look at this, this is an implementation of this algorithm. So I put it all together, and this is an implementation in Octave. And there is bookkeeping things, etc., etc. There is bookkeeping and things to do and installing things, etc., etc. But once you do it, it's basically 60 lines. Okay. And I mean, I took away a few comments. I mean, in the real program, then it has lots of comments, etc. But I took away the comments to make it fit into one page, just to show off a little bit, right? And you know, so this is a program that you can tell the students to implement in homework, and they actually do it. Okay. And so with a little bit more sophistications, this is something that we kind of computed. So, and I apologize, another factor. So this would be, yeah, well, I put over here the EPS, it's okay. But anyhow, so this is a very famous example, and then you try to look for the golden mean and so on, and then you can use this algorithm to find the places, to find the, I mean, the omega is the counter term. So on these things over here, for different values of epsilon, we were finding the counter term, right? And this is how it looks like, yes? So this can be computed actually quite, so it's very constructive. And then the result stops being true when epsilon is equal to 1, because when epsilon is equal to 1, this function over here is not a diffeomorphism, so you cannot, do these things that I was telling you, taking derivatives and inverting them, doesn't work. And this is actually what happens when you take the several Arnold terms for many different numbers. I mean, once you do it once, computers are very good about doing it for everything and so on. So we actually did, like, I think it's like 10,000 of them. The algorithm is very fast, so you can do a continuation method. And this is an amusing picture because you get all these Arnold terms for very Diophantine numbers. And this is one of the things that we will show, is that all these lines, so you have a bunch of vertical lines going from the bottom to the top, from epsilon equal to 0 to epsilon equal to 1. And so then you get a bunch of lines and they go from a set of measure 1, and at the end then you get measure 0. So there are infinitely many lines, all of which are analytic. And turns out that once you look into horizontally, they are C-infinity Whitney, but nevertheless they manage to send a set of full measure into a set of measure 0. You can construct these things. It's not very difficult to construct these things if you don't require the Whitney differentiability in the middle. With Whitney differentiability in the middle takes a lot of effort to do it. I mean, I don't know, I have not. But anyhow, so that's a curiosity, but it's a curiosity that appears in reality. I mean, there are even worse examples, but this is one of the things that tells you that at the bottom, the Fubini theorem is a little bit subtle. So let me try to now prove that this is a method that I have motivated kind of heuristically, right? So you try to get all these things. But then I want to sort of try to prove that this system, that these things converge, and that these things converge, and that they give you a good algorithm. And then I will go into several stages. So the first step, I will estimate the corrections, which is what I call the linear estimates. Then I check that the estimates indeed reduce the error. And then there is iterating, so that you can produce all these, you can keep on repeating till you get all these things that they are optimal, okay? So in the linear estimates, then you make some assumptions, and the assumptions that I make, and I put them in blue, is that the derivative of this and the derivative of this is small, and then this average that I am dividing, it's also small, okay? And then you get estimates in the corrections, and they are very trivial in the sense that the only thing that you need to do, you remember the way that I obtained the sigma. The sigma was obtained by multiplying by this and taking the error, multiplying it by this and dividing it by this one, right? Okay, so that was the only thing. So the estimates of sigma are the same, and the estimates W, if you remember, W was obtained by solving a cohomology equation. I was putting it over here, so W was obtained by getting this cohomology equation. And then you have to multiply by the sigma, and then you have to take the V. So that's the estimates that you get, right? Not a big deal, and so on. The C new to the delta to the minus alpha, and I was putting alpha because I didn't, depends. If you want to believe Rusman paper, then you have to put, you can put a tau, but if you believe only the trivial estimates, then you put the C to the minus tau and the tau plus the D, etc. And now you need to put the nonlinear estimates are more complicated, because the difficult thing is that you need to ensure that f of h plus delta makes sense, and that you can use the Taylor expansion on the to order 2. And then this requires that this h plus delta gets mapped into the domain of f. And this requires one assumption, which is non-trivial, which is that the estimates that the things are mapped inside of the domain, and then delta is not very small. Sorry, delta is not too small, because if delta is too small, then the corrections are very big, and then you get out of the domain. Okay. And now, if you look at these things, then you can prove that h plus whatever is in the domain of delta, in the domain of f, and then you can do this composition, and that this is very well inside, so that you can have a distance. And now the estimates of the new error, which I denote by tilde, is very simple. So this is the new error because this is the functional equation evaluated at delta plus sigma minus f, etc. Right? And now there is an orgy of adding and subtracting, right? So I add all this line here, but then I subtract it. You see, I subtract it, and I subtract this other part in there, right? So there is a lot of subtractions that I put, right? So. And some of the terms are color coded in red and some of them are, so this is just these things over here, except that I add and subtract several other terms, right? Okay, I add and subtract, I add this term, but I subtract it, and then I add this term and I subtract it, and the rest are the terms that appear here, right? So this is just adding and subtracting. But then the interesting things that I have over here is that once you do all this, right, this term over here is very easy to recognize because it's going to be estimated by the Cauchy estimates. And then these terms over here, the ones that I put in red are the error, and then the sigmas are the other terms that appear in the linear equation. So the only term that doesn't survive is this DEW that I had. I mean, the sigma and the delta were chosen in such a way that they killed these things more or less, except for this other term that I have been arguing that it's small, right? Yes? So that's kind of the crucial thing, that the terms in red are the error, the terms in red are the error, right? And the sigma and the delta were chosen precisely so that they kill the error as much as possible, except for this term that they don't kill. Yes? Right? So this is beautiful. And then, well, once you get these things over here, so the only term that survives is this Taylor order expansion, right? So there is this Taylor order, there is these things over here which can be estimated by delta square using the Taylor expansions up to second order. And then there is this pesky DEW, which can be estimated by the derivatives of dE, which is using Cauchy estimates, and then there is this W, which is obtained by these other terms before. But the interesting thing is that you get estimates that depend, I put them over here, there is this square of the things over here, but the interesting thing is that the error appears square, and then you get delta to a power 2 to the A, and I changed the letter A because there is the Cauchy estimates, and I didn't want to keep track of all these things over here, right? Okay, so that's basically like the things that you get from the W and so on. So I mean, as I told you, I am trying to simplify things as much as possible, not obtaining, so I sacrifice sharpness for simplicity. And then you want to estimate that you get, you can want to show that you can repeat the steps and converge, and then of course the condition numbers remain in the control. So from the moment I will do the estimates, I will just build some safety margin that I do the bad terms, I make them twice as bad, right? Like the distance gets to be 1/2, and the M's, which is the things that measure the non-degeneracy, etc. So I will do all the estimates using these things over here, and then at the end I will show you that you never leave these things over there, right? All right, so the first thing to do, let me just not mess around too much with the choices. I mean, if you want to mess around with the choices, then you choose the loss of domain, so you're going to be losing domain at every step. And then I choose the loss of domain to be like a power, decreasing like a power. And then this is the things that you get. And then I use a notation, which is that the error in the row n is basically, I just write it as epsilon to the n. And the key estimate tells us more or less the following. So this tells you that epsilon to the n plus 1 is equal to c. And there is a power that it's obtained by taking the 2 to the n to a power and then epsilon n squared. So let me write it in this way. Okay. So these are the quadratic estimates, and then I want to sort of do something which is really very wasteful, but this allows me to get done very quickly. Okay, so the thing that I want to do is to get done, think of this as a contraction. So if I can show you that if beta is very small, so that this is smaller than beta, then you obtain, I mean, if all these things is smaller than 1, if all of this is smaller than beta, I can prove these things, right? So I get to treat this. I mean, of course, this is a horror because, I mean, you can get much more subtle estimates, but I am going to just treat all this like a contraction, okay? But it works and you can explain it in 1 page rather than taking 2 pages. So, you know, I am, right? So this is kind of a, so this alpha is known, and the thing that, and then if you give me the alpha and then you give me the C, which I have, right? And you give me the alpha, you give me the C, and then I try to find the beta in such a way that this is true, okay? And then once you look into these things, you look at the corrections, and the composition condition is ensured if this is the error C alpha to the n is less or equal than whatever, which is one smallness condition in beta. Remember that alpha is known, and to ensure that how much do the domain changes? Well, the domain changes by something that is bounded by the size of the step, which is C alpha n to the beta n. So this amounts to another condition, right? And then to estimate the deterioration in the m's, then you have all these things over here, right? But the interesting thing is that if the beta is sufficiently small, then you can ensure that all these things are over here. And how small does need beta to be? Well, there are 3 conditions, okay? And you have 3 conditions, so you find your beta and then you find your epsilon in such a way that, that this condition is satisfied, right? So that's the only thing that you need, is that the induction assumption at the first step is satisfied. So that's all that there is to it. I mean, it's a little bit tedious and I am running a little bit fast, but it's, if you sit down, then I claim that you can understand it all very quickly, right? And so this tells you that then all these things can be done, etc. Now, of course, this is a little bit of a horror because I was obtaining exponential convergence. Actually, everybody knows that the convergence is better than exponential, but it will take me 2 pages to sort of explain why. But it is done in the Moser's paper, or in the videos, or in the tutorial. I take a little bit more time and I do it, etc. I am a little bit afraid of time, but I started a little bit later, etc. So, all right, so this is the story. And then, yeah. So, I mean, once you look into these things over here, right, in this paper, I show you the figures of this paper. So we implemented this algorithm with a little bit more of care, and then you get all the way to the bottom, to the place where the things break down. And when the things break down, lots of very interesting things happen. Or seem to happen. There is no rigorous proof of many of the things, but if you want a catalog of the monstrosities, then there is this paper with Alejandro Luque, which, I mean, it was I mean, I had lots of fun and I learned a lot of things, etc. Different algorithms, different extrapolations, etc. I mean, when you want to go to the bottom when things stop to be true, then you have to be very careful about things. So let me give you a slightly more general point of view, which is that there is these things, and actually Alex Arrow will be trying to using it over here, so that basically what we have been discussing is that you have a functional equation. You have a functional equation that you try to solve, and then you need an approximate solution in one norm. And then and then you have to check a few condition numbers, right? And if the error is sufficiently small compared with the condition numbers, then there is a true solution nearby. And then the things that are missing, unfortunately, in the things over here, is that I can bound the error between x0 and the x star. I can bound it, but in a slightly different norm. And this is one of the things that happen with the hard implicit function theorems. Other than that, it is exactly what you would expect in the contraction mapping principle. In these hard implicit function theorems, the things that happen is that you have to go from one norm to another. And anyhow, and the interesting thing is that once you have these a posteriori theorems, like the theorems that I just proved for you, is that you don't need to justify how you got the approximate solutions. The only thing that you really need to verify are estimates on the error and in the non-degeneracy conditions. And this is actually quite easy to do. And then, of course, this is what is going to be done by Professor Arrows in his lecture in 2 weeks. Okay. And this is more or less the thing that I was telling you, that if you have one of these a posteriori theorems, then it tells you that your computations are correct, even if you are very close to the breakdown and the things look crazy. So if you want to prove, I mean, you know, if you want to sort of prove that pi is less than 10, then you can use almost any numerical method. But if you want to prove some things that are getting really weird, then you really need to sort of, I mean, convince people that things are okay. I mean, the perturbative expansions, even if the series diverge, then they give you good results, because you are proving things that everybody believes, right? I mean, and that you can see. But if you want to go into the unknown, I mean, if you are, you know, if you are climbing the stairs in your house, then you can do it with your shoes. If you are climbing the wall of the Matterhorn, then you need a lot of good shoes, and then you need safety measures, right? I mean, if you want to do trivial things, then you can do them with any method. But if you want to do really difficult things, then you need safety measures, etc. And anyhow, so one of the interesting things that I want to tell you is that if you have these a posteriori theorems, then you can take sort of approximate solutions and justify them, and then they tell you that they are small things over here. If you want to get differentiability, for example, with respect to parameters, then you can get it because you guess the expansion of the derivative, and then you can get the expansion of the derivative, and then this is okay. And then if you want to prove analyticity, proving analyticity is exactly the same as proving differentiability if you can work with complex numbers, right? And that's the way that you prove that this series converges in the counterterm method. Then you prove that the series converge because you guess a derivative, and then you prove that the guess of the derivative exists, and then you prove that all this works with complex numbers, and then you prove analyticity, and then you have analyticity, and then things converge. If you want to prove that this traditional series converge, that this traditional series diverge, then it's very easy, because then you check what is the formula for the derivative, and then you see that you cannot get any formula for the derivative when the rotation happens to be rational. And that's the argument why the series converge. Okay, and then I wanted to maybe make a remark about finite differentiability, that there is a trick that was done by Jürgen Moser and improved by Eddie Sender in '75. This is a very curious lemma for real analysis people. So in my opinion, it's very beautiful because it sort of because it tells you that it gives you a link between the real analysis and the complex analysis. So this tells you that a function is differentiable, and unfortunately this works only for fractional differentiabilities, right? It's false for complex, it's false for integer differentiabilities if and only if you can find analytic functions that approximate it. And unfortunately this should be a phi. Sorry about that, this should be a phi. So there exists a phi n, and the things converge on the reals. And then the interesting thing is that these functions in the complex, they converge very fast. And this is assumption. And if you take this, then you can take the analytic results in an a posteriori format and convert them into finite differentiability. So that's the trick that was used by Jürgen Moser. And once you have that, maybe I don't know if I mean, I wanted to make propaganda to several things like this. There are several things that you can try to do once you have all these things, like I mean, this algorithm that I was describing, I described it only for maps of the circle. And if you think about it, maps of the circle, this business of using the derivative doesn't work when you go to higher dimensions, but it works if you go into higher dimensions, if you have some geometric structure to give you control in other things. Actually, this is one of the beautiful of the things of symplectic geometry. So in symplectic geometry, if you have information about half of the variables, then you can get information about the other half for free. And this is something that we use actually quite a lot in other contexts, like for example, in this business of scatter. Once you study perturbations, there are fast variables and slow variables. And if the fast variables, so the fast variables are very hard to control when you have the perturbations, but the slow variables are easy to control. But if the fast variables are conjugate to the symplectically conjugate to the slow variables, then you can go from one to the other very easily. So this is something that we have used in other contexts, and this is actually quite useful. And then I wanted to make propaganda for several open areas that are kind of interesting. And then in infinite dimensionals, then we will get the lectures by Yachi Yang in a couple of days. And already, I mean, if you look into the papers of Jürgen Moser in the Pisa lectures that I was describing in '66, then you have lots of applications to PDEs. In evolutionary PDEs, this is something which is a little bit new and something which is completely open, in my opinion, which is the things that happen at the boundary of validity. In one dimensions, people know quite a lot of things, but when you are in the twist conditions, but if you take away the twist condition, or you go to higher dimensions, very little is known. And then, so there is other things that happens. I mean, so as I told you, the things that are quite interesting is this business of resonances. And then Marian Gilea will be explaining about what happens when these Diophantine conditions are violated in a very bad way. So when you have rational relations, then new phenomena appear, and actually this is very interesting. And then there is also another area which I believe is very important, which is, I mean, people have always been telling, oh, you know, okay, YAM is something very theoretical and doesn't apply because it requires very small numbers and these sort of things. Well, and nowadays things are changing quite a lot. And then, as I was telling you, one can get numerics and the requirements of regularity and the small numbers are all going away. This is the things that people say. I mean, if you say these things, it's like if you are wearing last year's shoes. I mean, you know, don't say this. It looks like you're an old-fashioned person. And then there are quite a number of new type of things, because I mean, so if you study celestial mechanics or oceanography, then you have to take what nature gives you. But there are quite a number of other things, like when people are constructing accelerators or plasma devices or ion traps, in which the problem is not to study the things that nature gives you, but to design. So you have to choose. So these things that I was telling you, choosing parameters and things like that, is something that people can do. So when you are when you are trying to study what happens, right? I mean, the mass of Jupiter is what the Jupiter decided, right? And the mass of Neptune is what Neptune decided, but when you're designing accelerators, you can design the shape of the magnets, you can design how much current you put in the magnets, etc., etc. So that's a totally different problem, right? Okay, so this business of choosing parameters that at the beginning was kind of like a device, it's actually something which is very, very real. And this kind of requires new mathematics. Anyhow, so I think I will stop here, and I am a little bit over time, and I apologize, but I was, so thank you.
Okay, Javi, people have right to unmute themselves.
Yes, so feel free, anybody, to unmute yourself and ask any question to Rafa if there are questions or comments.
I had one question, Rafael. It's about in what you showed, the difference between the Linstedt series and the regular series. So I guess I didn't see really what or can you explain a little bit more what the difference is, and to which extent, if you're changing the equation, this is still the same problem? And also, I think you're muted.
You're still muted, Rafa.
I can. So can you hear me now?
Yes.
Yes.
Okay, so in the typical series, is what people do is so you have a system, and the system has a frequency, and then you have to find the frequency, and the frequency changes with epsilon. In the counterterm method, what you do is that you change your system, whatever you need, in such a way that you keep the frequency fixed. Okay. So when you change the frequency, so you see the thing that happens is the following. The philosophy is that when you have the frequency and you have the frequency to be Diophantine, this is good. And when you have the frequency to be resonant, this is bad. Okay. And if you allow the frequency to change in epsilon, then you have to go through regions where the frequency is going to be extremely resonant, and this is very bad. That's why it basically things are bad. Yes?
But so do I understand it correctly that you're saying that you won't really be solving the problem that you were given, but you just say that but I can find instead another problem, which is f plus a constant.
If you want to say it in this way, yes.
Okay.
But this other problem is a little bit, so there is a trick that I didn't discuss, but you can go back to that. Yeah, that's, I mean, depending on who gave you the problem, right? But if they give you the original problem, yes, you're solving the wrong problem. But if, as I told you, these things over here are the problem that is given to you very often. So, for example, if you are designing an accelerator, if you are designing, say, an oscillator, or you are designing whatever to do a radio, right, which is the things that they are telling you, that's exactly the problem that you want to do. They give you the frequency, and then you have to construct your circuit in such a way that it emits in the right frequency. Okay, so you're absolutely right that this doesn't solve all the problems in the world, but and some of the problems, if they give you to understand the other problems, it may be even unsolvable, right? It may be even false. So let's say that this solves the problems that are that sometimes appear in practice, and it solves the problems that are right. And this is a point that I want to emphasize, which is that. I mean, you can write problems that don't have a solution, and then, of course, let's not do them, right? But you're absolutely right that the thing that I want to emphasize is that you have to be careful, and some of the problems that you pose may be unsolvable and may be false.
So is that what you were talking about at the beginning when you said instead of starting from a problem and finding all the solutions and then selecting the one that are quasi-periodic, I'm going to start with the quasi-periodic and then somehow select the problem.
That's right. That's right.
Okay.
And you can go, and this is something that Alex Saro will tell you a little bit. I mean, this is a little bit, in the case of circle maps, it looks a little bit artificial. But in the case of Hamiltonian system, choosing the parameters comes out to be choosing the initial conditions. So it's a little bit better. So you can choose the initial conditions so that in the case of circle mappings, it's a little bit more artificial somehow, or sounds artificial maybe. It's not artificial depending on where you are. But in the case of Hamiltonian systems, as you will see in Professor Aro's lectures, it's very, very physical. It's choosing the initial conditions.
Good,
choosing the initial conditions. In other problems, then it's, and even in this case of circle mappings, is not totally stupid in the sense that I have seen it done in when people are constructing oscillators and people are constructing antennas, then people have these things that they tell you which frequency you should be emitting, and then you can put whatever elements you need into your, you can tweak all the things that you want in your antenna or your anything in such a way that you get the circuit to emit in the right frequency, right?
Thanks.
Okay. More questions or comments?
Yeah, and I'm thinking that this is one of the things that I believe are getting to be in the cutting edge, because I was talking to several other people, and the design problems are now becoming much more doable. I mean, you can go from one parameter to another. You can use the implicit function theorem and go from one to another once you have done the right. I mean, even if you're solving the wrong parameters, then you can choose the right parameters with the implicit function theorem. But on the other hand, more and more, the physical problems are problems of design. That is happening nowadays. I mean, people that are constructing ITER, they have hundreds of parameters. I mean, they don't, you know, they can choose how much current do they put or how much whatever, etc., in order to get the effects that they want.
But then, I mean, can they really choose the number to be exactly Diophantine? Because it would seem to me that then you change the omega by just a tiny amount.
Yeah, the thing is, that's a very, very good question. How can you make all this constructive? And the answer is that that's why I was telling that the things are not completely ridiculous if you do the frequency, because even if the number is not Diophantine, but it agrees with Diophantine, say to 20 figures, then the things are going to behave like Diophantine for maybe 10 to the 20 seconds, and then that's perfectly good. So you can go back into the other order, right? Like, how can you know that the frequency is not the right frequency? I mean, you see, well, if the frequency, I mean, you're a pessimist in the sense that you're telling me that if the number is not exactly Diophantine, then if the number is not, I mean, it's a rational that is very close to Diophantine, it's still rational, etc. So that's the thing. But you can look at it in the other direction. So if the frequency is close enough to Diophantine, then things are going to remain the same for a very long time. And you know, and if so, you can argue both ways. So you can argue in the sense that all this theory that you develop for Diophantine numbers is going to be true for non-Diophantine for a very long time.
Okay, that's fair.
More questions or more comments?
And you will see that these parameters that look a little bit mysterious, if you apply implicit function theorems, etc., especially in the lecture of Professor Aro in 2 weeks, then it's just basically choosing the initial conditions. And this is very, very fair and very, very, you know, people that are in aerospace when they are designing missions, etc., that's where they spend the time discussing. I mean, what are the initial conditions for the launch and what are the initial velocities, etc., etc. So it matches perfectly well.
Okay. So let's thank Rafa again, and we'll reconvene in 10 minutes.
It's good.
In the same link.